Hi and welcome back. Today we're going to start looking at ionic bonding and building on that steadily over the next few videos. So let's get started. First of all, the key things that we need to keep in mind as we go through this, and these are the key knowledge points that we're expected to know from this unit. We want to be able to identify the common properties of ionic compounds, much the same as what we did with metals, and you may be familiar with these from previous studies. So this includes brittleness, hardness, high melting point, the difference in electrical conductivity in the physical states of being a solid or a liquid, the uses of these different ionic compounds in different areas of society, how we go about writing empirical formula of ionic salts, i.e. ionic compounds, and how we go about naming them. And you should be able to, by the end of this unit, be able to comfortably write the name from a formula or the formula from a name as we move forward. So ionic compounds are what we refer to as salts in chemistry. These are often seen as gemstones or copper sulfate. They generally have a crystalline form. As we talked about earlier, the properties of a compound can tell us a lot about its structure. So if we think about ionic compounds where sodium chloride, NaCl, sodium chloride, which is table salt, is 1, it helps us think what those properties would be. If you think about rock salt that you probably have seen from the supermarket and things like that, it helps us to get a bit of an idea of what those properties might be. Ionic compounds are very, very common everywhere throughout the Earth's crust. They're composed of different minerals. They make up gemstones, different ores, so things like bauxite and things like that that you looked at with processing of metals. They're actually ionic compounds. The properties of these compounds have led to the development of the ionic bonding model, just as the properties of metals led to the development of the metallic bonding model. The use of these compounds is quite prevalent through our society. We can use them for different additives, food additives, salts. We use them in electricity production in our batteries, and you even find a large number of ionic compounds in our body. So things like calcium phosphate in our bones. We find limestone and sandstone in buildings that we use for building materials. The high melting temperatures that we see of ionic compounds, see them being used to line furnaces or used for ceramic engine parts where high temperatures may melt things like metals and otherwise. The electrical conductivity of these in the aqueous state, not in the solid state, have seen them being used inside batteries in devices that you're probably familiar with. So particularly lithium-ion batteries are used for a higher voltage in our devices these days. Of course, you've probably come across baking powder. This is an ionic compound that decomposes to give off CO2, so it's often used as a raising agent if you do any baking or anything like that. With the bonding between atoms, you may recall that we have 3 main types of bonds. These are metallic bonds, which we have already looked at, ionic bonds, which we're looking at now, and covalent bonds, which we will look at a little bit later on. Depending on the type of bond that a substance has, will tell us some of the properties that we can expect from that material. One way I like to remember the type of bonding and figuring out what atoms would be involved in it is to use kind of like a bonding Punnett square, and you may remember Punnett squares from year 10 genetics. But if we put metal and non-metal down the sides, which are our 2 options, and across the top, if I cross a metal with a metal, it will always be metallic bonding, and that's the only option that will ever give us metallic bonding if it's always only pure metals. If I have a metal combining with a non-metal element, I will have ionic bonding, and that happens quite a lot. You can see that we can combine any non-metal with a metal, and we get 2 options in our Punnett square. where we can end up with ionic bonding. And then the last one is non-metal with non-metal, where we end up with a covalent bond. But for this topic, we're concentrating on this metal and non-metal combination, which gives us an ionic bond. You may recall that the formation of ions is due to the loss or gain of electrons. Okay, so a neutral atom gaining or losing electrons in order to complete its outer shell, to have 8 electrons in its outer shell. If an atom loses electrons, remembering that electrons are negative, it will become positively charged, and we call this a cation. So we see this with sodium, where sodium can lose its 1 valence electron to give us an electron configuration of 2,8. So you may remember 1s2, 2s2, 2p6. So our 2 subshells in our second shell are full. By losing an electron, I now have more protons than electrons, so the atom becomes positively charged. In the case of anions, when an atom gains electrons, it becomes negatively charged and is now known as an anion. So if we look at something like chlorine, which has 17 electrons, okay, we need 1 more to fill that outer shell position, which means that it will get 1 more electron, meaning it will have more electrons than protons, remembering that chlorine is an atomic number of 17, so it has 17 protons. If it gains an electron, it's going to have 18 electrons. This means that it has more electrons than protons and will have a negative charge, and we call that an anion. If we think back to the unit we did on the periodic table and we talked about electronegativity, the ability for something to draw electrons to itself, okay, the higher the electronegativity of an atom, the more likely it is for it to gain electrons. So things that have a high electronegativity, such as our non-metal atoms, they will form anions. Things that have low electronegativities or highly electropositive, such as the metals on the left-hand side of the periodic table, these lose electrons easily and will form cations. When we refer to the term electrovalency in chemistry, we are referring to the charge on the ion that occurs when an atom loses or gains electrons. So if we go back to that example where we said that sodium loses an electron to form a cation, the cation of sodium here will have an electrovalency, using that term, electrovalency of +1, which is equal to the charge that we see on that ion. Whereas our example with chlorine, where it went to chloride and we formed the negative anion, this anion will have an electrovalency of -1. Okay, so that electrovalency is referring to the charge of the ion. If it's a neutral atom, it will have an electrovalency of 0. It won't have a charge at all. So as we know, the electronegativity of elements increases as we go from left to right, with fluorine being the most negative. So these guys over here are going to form negative ions. Okay, they're going to form anions. And we see those anions being formed as -1 in group 17, -2 in group 16, -3 in group 15. Group 14 doesn't tend to form ions, and now you can see that our electronegativity has dropped off quite a bit. We've hit the metals again by hitting boron and aluminium over here. So in aluminium, boron has actually got some interesting chemistry, and we see him with covalent compounds later on. But starting with aluminium, we're going to have a +3. Remembering our transition metals can have a varying charge, and then when we get over here, we're going to have +2 and +1 charge on our ions, because our metals are electropositive and will give up electrons rather than holding on to them or gaining them. So when we look at common atoms, if they're going to be in group 1, like sodium, we only need to lose 1 electron in order to complete its octet.
Okay, so when we lose that 1 electron, we will have 10 electrons compared to the 11 protons of sodium, giving us +1. Chlorine has 17 protons, 17 electrons. In order to complete its octet, it needs to get to 18 electrons. So we will gain an electron. This gives us 1 more electron than protons, making our electrovalency -1. So this would be a cation, and this would be an anion. When we look at the electron configuration, we will often still see things using the Bohr notation from year 10 and lower levels. Just remember that you should be using subshell in year 11 chemistry. Metallic atoms are always going to form cations. They have low electronegativity, so they will lose electrons. So where in the periodic table is will tell you which ions it is likely to form. So the number of valence electrons will be the number of electrons that it's going to lose. For group 1, this will be 1 electron, so group 1 will tend to form +1 electrovalency ions. Group 2 will form +2. Then we skip over the transition metals because they can have varying charges, and group 13 will have +3. These are the main ones that we can read from the periodic table in terms of cations. For negative ions, because they're non-metallic atoms, they're going to be gaining electrons. Again, this will change their electron configuration to be the same as the closest noble gas. So you may remember that if something has the same electron configuration, we call this isoelectronic. So ions will be isoelectronic with their nearest noble gas. So for the case of oxygen, it has a 2,6. It needs to get 2 more electrons to complete its outer shell to be 2,8. This will mean it has 2 more electrons than protons, making it a -2 charge. So you'll notice that oxygen is in group 16. So group 16 will add 2 electrons to get to group 18, which are our noble gases. So it will be -2, -1 for group 17, and -3 for group 15, because we need to go 1, 2, 3 electrons to get to our noble gas configuration. Each electron is going to be a -1, so overall we will have -3 on those anions. So this is a diagram that just summarizes that. You'll notice here that group 14 is +4 or -4. These typically, the non-metals here, typically don't form ions. Okay, they tend to only covalently bond. So we will not be seeing like +4 or -4 carbons or silicons. But tin, you can see down here, tin, lead, these will form +4 metals, okay, both tin and lead in terms of that. And the other transition metals are all variable oxidation states, so they can form multiple different, maybe like copper, we can have +1, +2. There can be varying oxidation states. Manganese can be +2, 0, +4. We can see different conditions giving different valencies to these elements. When we talk about atoms forming ions, the reason they form ions is stability. Okay, this means that they're more stable with a full outer shell configuration. So atoms will tend to gain or lose electrons to reach this stable configuration. Metals will lose electrons because they have a low electronegativity. Non-metals, which have a higher electronegativity and higher ionization energies, will gain electrons to complete their octet. One of the reasons I love this is if you think about it, if we take something like sodium metal, which must be stored under oil because it's so reactive, and chlorine gas, which on its own, if we were to breathe it in, would poison us, it's highly toxic. If we combine these two, this metallic bonding that we see here, and the covalent bonding that we see in Cl2 molecules, if we combine these with a catalyst, we get a very exothermic reaction. Okay, we get a quite a big chemical reaction. The sodium will lose one electron, and the chlorine from the Cl2 will form chloride by gaining an electron. So that electron is going to come to the brane, and we will form sodium chloride. We'll get salt. So we can see in this simple example that the type of bonding can really change the way something behaves. We can take an explosive metal compound that will on water react explosively, combine it with a toxic gas, and we get something that we essentially flavor our food with, so it becomes non-toxic and able to be eaten. And this shows you the power of the way that the bonding can change the properties that we see. So ionic bonds are formed between metals and nonmetals. It is a transfer of electrons. So something is giving up an electron and something is accepting an electron. Then we see electrostatic attraction between the positive cations and the negative anions. And that attraction is what we see and call the ionic bond. We can show that by a diagram where we use an electron shell diagram and use arrows to show the transfer of the electrons. So in this case, we're seeing the transfer of this valence shell electron from sodium to chlorine to form the sodium ion with the new electron configuration, the chloride ion with the new electron configuration, and these are drawn closer together to show the formation between the newly formed ions, that electrostatic attraction. When we look at something like magnesium, magnesium has 2 valence electrons. It needs to transfer 2 of these to form a stable octet. If it is forming a compound with something like chlorine, one chlorine atom will take 1 electron because it only needs 1 to complete its octet, and another chlorine atom will take another electron. So in this case, I can see that I need 2 chlorine atoms to form a stable bond with magnesium. So we get the formation of magnesium chloride, the new ionic compound. So the structure and properties of ionic substances come about because of the unique way that these ions then interact in the electrostatic attraction between them. They will arrange themselves in a 3-dimensional crystal lattice. The lattice is then held together by strong electrostatic forces. The ions in the lattice are packed so that the ions of the same charge are kept as far apart as possible. This is known as the ionic bonding model, and in our next video, we will talk about how the properties of ionic substances relate to this model and how we can explain them in terms of the model. I hope that makes sense. Make sure that you have taken clear notes on the formation of ions, which atoms form what type of ions, and I'll see you in class.